Now, unfortunately, Christine, who is watching this at home, won't be able to see the actual pig flying. So maybe one of you guys could record it and just show her what the pig looks like.
Christine.
Okay, so I'm going. Yes, I mean it is a real fetal pig flying around the room, right, everyone?
Yeah.
So it says,
That's so cool.
when an object travels at a constant speed along a circular path, we say it has uniform circular motion. If its speed were changing, then its motion would not be uniform. Any object moving in uniform circular motion is accelerated toward the center of its circular path. This acceleration is called centripetal acceleration and equals v squared over r, where v is the speed and r is the radius of the circular path. Since the net force on any object equals ma during uniform circular motion, the net force, called centripetal force, equals mv squared over r and is directed toward the center. This is what happens when an object suspended by a string moves in a circular path. So this thing here is called a conical pendulum. A regular pendulum, like a grandfather clock, just does what? Just goes back and forth like so, right? So this guy is not going to fly back and forth. He's going to fly in a circle. So he's what's called, or she, I don't know Floyd's gender.
It's a guy.
Yes, it's a genderized pig. Is called a conical pendulum. The string of a conical pendulum sweeps out a right circular cone. In this experiment, you will measure the speed of an object that is comprised of a conical pendulum and show that the net force is indeed mv squared over r. So we're just sort of verifying this, that's all. Okay, so pre-lab analysis. Draw the force vectors, a free body diagram, that act on a conical pendulum. Ignoring air resistance, note there are only two forces that act on the pendulum bob. In this case, the pig. So his name's not Bob, it's Floyd.
Well, why does it say Bob?
Well, a bob is like when you, if you've ever done like a...
Fishing?
Yeah, there's bobs, right? But that's a different idea. It's something that sort of holds things vertically, is a bob. Yeah. So draw the force vectors, a free body diagram that act on a conical pendulum. Ignoring air resistance, note there are only two forces that act on the pendulum bob, in this case the pig. One is mg, the force of gravity, and the other is the string tension. So do you have this picture?
Yes.
And do you have it labeled?
Yes.
Oh, you do? Okay, well, okay, so that's good. So then step 2 says, with dashed lines, show the horizontal and vertical components of T, also label theta between the tension T and the vertical. So let's draw in, let's go this way, I think, and we're going to label this one TY, pi,
Whoa.
right? That's the Y component of the tension. Maybe that's why Kai got his name. He gives his mom and dad so much tension. No, that was pretty poor. But it's been I've been waiting for a lot of years for a tie in grade 12 just to make that joke.
Are you sure?
I should have practiced.
It's first time I should have practiced to make a better.
I should have. Okay, this one over here, of course, would be the TX. And label the angle theta between the tension T and the vertical. So that would be this angle right there, right? Would that also be equal to, would that be equivalent to, if I draw it on this side, would that theta be equivalent to there? Maybe that might be better, right? Is that what it says on the next page? Maybe we should have drawn it like that one. So the TX is sideways and the TY is up and down, right? Normally I do this on the board, but I'm going to do it up here because I've got to record it. Okay, so then it says, step 3, does the pig accelerate in the vertical direction? Now I haven't actually shown you this thing flying yet, right? So let me just turn his wings on. Now, was it not worth the wait?
Yes.
You will notice,
Why?
that it's actually maintaining a pretty constant circle, isn't it? It does eventually, but for a good period of time, it actually stays pretty uniform. Now, interestingly enough,
When pigs can fly. Whoa.
when pigs fly, exactly. If I get them going without the wings, what's going to happen?
Oh.
But what do you notice?
Boring.
So it actually goes slower. It slows down quite a bit, right? So the wings are actually doing something. The wings are actually doing something. I've never really figured out what it is, but it actually keeps it going.
Believe me.
Okay. Oh yeah, if I just do this, just yeah.
But he is moving in a circular. Let's go.
He is, isn't he? You know what? I've never thought of this. Okay, so this is interesting because there is a thing called you guys know. Well, you don't yet. Conservation of momentum, which is what we're going to use soon. This would be conservation of angular momentum. So he is spinning, right? So when he does that, he's creating a torque, a momentum in one way. So when I spin it like this, that must be what actually keeps it going.
Wait, spin the other way. What happens when you spin that?
I don't know. I've never had it go the other way.
Oh.
I always spin on this one.
We'll spin it the other way.
I don't know.
I think it will work.
That was a bad first thought.
That was
But look, he's stabilizing, so.
Oh.
Whoa.
He goes a lot faster.
Hey, it's not bad.
Oh, a lot faster.
See, doesn't this totally work all the work?
Yes.
Just now, please,
And Mr. Bennett.
please don't share this with grade 11.
Play tetherball with
I
him.
should take it off. Oh. I'll just, yeah.
Because we want it to be a surprise for them.
Story maybe.
What?
So if we were to shove something lighter to that, those wings would it like
I don't know.
would it actually fly or no?
Straps up. Oh, like, I mean, like if we just put like a little army man or something. Probably not, no. Okay, so anyways, step 3, back to the science. Step 3, does the pig accelerate in the vertical direction, up and down? No. So what does this tell you about the magnitude of the vertical component of T and mg? So the Ty is actually, like, remember it's like this, right? There's the pig. This is Ty. So the Ty, because it doesn't accelerate vertically, the Ty has to be equal to the mass times gravity, right? Ty is equal to mass times gravity. Step 4, does the pig accelerate in the horizontal or radial direction? And the answer there is yes. In what direction? Towards the center, centripetal force. Knowing that the net force in the radial direction for any object in uniform circular motion is the centripetal force, what does this tell you about the magnitude of the horizontal component of T and mv squared over r? Well, that says that Tx equals mv squared over r. So step 5 says, write an equation that shows how the horizontal and vertical components of T are related to the weight and the centripetal force. They give you a very strong hint because it's kind of confusing. Hint, tan theta is equal to opposite over adjacent. Well, if this is our theta, right here, if this is our theta, and this is Tx and this is Ty, opposite theta is our Tx, adjacent to our theta is our Ty. This is Tx over Ty. Do you guys have that?
Yeah.
Oh, you do. It's just really, really tiny, right? So the Tx is mv squared over r, and that's all over mg. And guess what happens?
Cancels out.
M's cancel. So we got v squared over r over g, which can be rewritten as v squared over rg is equal to tan theta. Now, does that look at all familiar?
Nope.
Yes. We did at the very beginning.
Is that not yesterday's banked and unbanked curve stuff?
Yeah.
Bingo.
Bingo.
Okay, so step 6 says algebraically solve for the tangential speed of the pendulum from your equation to. So what they're saying is solve this for v. Okay, so v is going to be, you're going to have v squared is going to equal rg tan theta, right? Which is the latest droid in the upcoming Star Wars movie.
What would you say?
RG tan theta.
Is he actually?
It's like the thing with the pig.
If you ever find yourself saying, is that actually true? Good chance it's not. Especially if I'm in the room.
Yeah.
So V equals what? As soon as Megan started saying it, she was realizing it. She couldn't stop it.
Yeah.
It's like had too much momentum, had too much inertia.
Is that actually true?
Oh my god.
I never mind. Square root RG tan theta. Won't you guys laugh if that's actually his name in the new movie?
It's just
That would be. Everybody good?
Yeah.
RV equals square root RG tan theta. Okay, so procedure. Set up the flying pig. Note that anything that flies in a circle here, whether it be a pipe, airplane, blah, 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 blah. I'm going to skip this quick. Okay, so once the pig is up and flying in a circle of constant radius, measure the radius of the circle as accurately as you can. Express your answer in meters. Now, normally I spend a fair bit of time helping people try to figure out, how do we figure out this radius? Okay? This radius from vertical, how do we figure out this radius from there? Normally we spend about 10 minutes on that. I'm not going to bother. We've tried numerous things over the years. The best way I've found is to take a laser pointer and hold it here and then measure. If you go into my old room, Mr. Smigowski's room, there's actually a mark in the ceiling. Okay? Yeah. So what I'm going to do is I'm just going to tell you, in the interest of time, because of our situation, I'm just going to tell you that the radius is 0.58.
Will it tell us in the test radius?
There won't be any test questions in this regard. We're just verifying.
Take
So,
a pencil to it and put a piece of paper underneath.
well, we actually tried. Someone suggested hanging a laser pointer from the bottom, and they thought that it would hang like this, and we could make a circle on the ground.
Ooh.
But it actually swung out too much.
Burn the circle.
And if it was too heavy, then it didn't come up. So it's a challenge. I guess you could, it would maybe slow-mo video and some paper, you might be able on a meter stick, you might be able to figure it out. But 0.58 has worked in the past. Okay? So we're going to say our radius is 0.58. And you're just going to have to trust me. Where is it? Where did it go? Oh, 0.58. Okay. Step 8. There are several ways to determine the angle the string makes with the vertical. Using your protractor may not be as practical as other methods. So here's the other thing we need, is we need to figure out what this angle is. Well, if we know this distance here, looks like the radius, and can we figure out the hypotenuse?
Yeah, sure.
Can you figure out the hypotenuse?
Yeah.
Yeah, that's just measuring, right? That's just a meter stick. So we can use opposite and hypotenuse. We can use sine, right? Figure out the angle. Okay, Riley?
Yeah.
So I've measured. This is 0.58, and I've measured the string to be 0.8.
98.
Okay? That's supposed to be a right triangle.
Oh, shoot.
Okay? So the hypotenuse is 0.8, that's the string length, and the radius of circle is 0.58. So we're going to say theta equals inverse sine of 0.58 over 0.8 to get our angle. Second function sine bracket 0.58 divided by 0.8. And you get 46.4. Shall we just say, well, we'll say 46.4. 46.4 degrees. Riley knows his pace. Say again?
All of your like QR code
You know what I said?
the decimals like
Oh, I know.
all the way down.
In the recording.
Whatever.
Lots of them are like
I know.
No, you don't have to.
Okay, so there's our theta. What did we get? 46 point. Come on. 46.4. Okay, so theta equals 46.4. Step number 9. Using the values for r and theta, you determine in step 7 8. Compute the theoretical speed of the pig using the formula you derived for the speed in steps 5 and 6. Remember, this speed is based on F net is equal to mv squared over r. So v is equal to square root of rg tan theta, I think, right? Okay, so that's going to be the square root of, the radius was 0.58. G, of course, is, do I need a minus 9.8 in there?
No.
It's going to cause problems with my square root. tan 46.4. So let's do that. We're going to take the tan of that value that I just came up with,
Shoot, my pencil broke.
and then I'm going to multiply by 9.8 and multiply by 0.58, and then I'm going to take the square root of that.
Trenton.
And I get 2.4 meters per second. Is that what you got too?
He's lying to you.
2.4 meters per second.
Pay attention.
Okay, so that is, based on our theory, that is the theoretical speed of the pig as it moves in a circle. So now we're going to actually measure the speed and see how close we get. Okay, we're going to measure the actual speed and see how close we get. So it says, in step 9 you calculated the theoretical speed. Now let's actually measure the speed of the pig and see how these two values compare. Since the pig flies in a circle, the speed is the circumference, 2 pi r, which is the distance, divided by the time t for one complete revolution. To make your measurements of t more precise, measure the time it takes the pig to make 10 revolutions and then divide by 10. So I need like 4 volunteers. Get your phones out, stopwatches.
I'm not a volunteer.
Okay, maybe 2, seeing as I can't get 4 of you. Okay, and I'm going to spin it, and once we get it going good, then I'm going to say start, and we're going to count
Oh, I don't need to
10 revolutions, so you don't need to stop.
Alright, cool.
Okay, let me just get Floyd going here.
Just, you know, my reaction time is really slow.
Okay, and once we're happy with this circle,
No! What?
not yet. Okay, so when he comes around last time, and ready, and go. 1, count with me, 2, 3,
4, 5, 6, 7,
When are we stopping?
8, on 10, 9,
9,
and 7.
10. Whoa, you lost control.
16.19.
got 14.
Yeah, because mine doesn't count because that's
Maybe.
16.19. Who else had it? 16.22. 16.
I need the phone.
Okay, can we just say that that's the average? That's pretty close, eh?
Yeah.
I mean, like, look, it's right. That's 3 away. Oh, it's in fact, that's exactly the average. So that makes a single revolution. 10t is going to be 16.19. So one revolution is going to be 1.6 seconds, right? Correct?
Yes.
Okay. Using your measurement of r, calculate the speed of the pig. So v equals d over t. The d is 2 pi r, so that's going to be 2 times pi times the radius, which was 0.58, divided by 1.6. So let's give that a whirl. 2 times, where's my pi button? Second function pi times the radius of 0.58. Divide that by our time of 1.6, and we get 2.3 meters per second.
I need a new pencil.
Not bad.
You want me to have a lid?
We know our pigs. Step 12, compute the percent difference between the value for the speed you compute in step 9 and the measure step. Use the calculated speed as the known. So remember when we did that in the projectile lab? Right? So we're kind of coming up with the percent error. So the percent difference is going to be 2.4 minus 2.3. So the 0.1 is the difference. And it says use the calculated speed as the known. So we're saying that the 2.4 is what it should have been. So we're going to take 0.1 and divide by 2.4, and we're going to express that as a percent. 0.1 divided by 2.4 as a percent times 100. 4% difference. Is that pretty good?
Yeah.
That's really good.
We had like 111 last time.
4%
Oh, yeah.
difference. Yes.
We did.
We had a lot of air resistance going on there, right? Now, this one here, is there some air resistance?
Yeah.
There is, because obviously if we don't have the wings going, it slows down, but it manages to keep it going in that constant speed. So there's just enough force somehow backwards, probably that conservation of angular momentum, to overcome the friction. So it's pretty cool. Yeah. Okay, so 4%. What else we got left? A couple last things. Oh yeah, post-lab analysis. What techniques for measuring R and theta would you recommend for best results? Listen to Mr. Bennett. What do you conclude about the magnitude of the string tension compared with the weight of the pig? Oh, but we haven't talked about this. So the string tension, remember it looks like this, right? There's the pig. There's mg. That's ty, that's tx. What can you tell me about the value of t compared to the weight? Will the tension be less than, the same as, or greater than the weight? And this is back to unit number 2.
Greater.
Why greater, rather?
Because tension's always.
Well, yeah, it is greater. Ty would have to equal mg, and this is the hypotenuse. The hypotenuse always has to be more, exactly. So the answer is greater. Right? The tension in the string is greater. And in fact, the wider the circle, right, like if it was way out like this, that would mean
More tension.
even greater tension. Now, do you think I can make him spin way out here?
But if they're all hard enough,
Really fast.
do it. Break stuff up. He was up there for a little bit.
He was, but he kind of tends to...
Well, gravity.
No. So I think what happens is the friction, air resistance slows him down, and he's only got enough of that angular momentum. It's always, literally, it's always exactly the same, every year. Maybe. Would that change the angle? I don't think it would change the angle. I think it would just do it.
I should do with a way bigger string than this.
It does have to do with that. It does. That is so cool. I never noticed that before.
Just leave it on until it stops.
Well, I put a fresh battery in today, so. Oh, like see how long it would keep going? It's gonna get annoying. That sound.
Not keep it up.
That was stop.
It won't last that.
Time for that.
What do you conclude about the direction of the net force that keeps the flying pig in uniform circular motion? Which direction is the net force? Did I miss one?
Always towards the middle or the opposite.
Always towards the middle, right?
Yeah.
Exactly. Toward the middle. Toward the center. Let's spell it the Canadian way. R-E. Toward the center. Oh, did I close it?
Why do we add a U in our color?
Oh, sorry.
Okay, last little bit. For uniform, okay, number four, for uniform circular motion, the centripetal force will always be less than, the same as, or greater than the tension in the string. So, like this, the tension is the hypotenuse, the centripetal force is the Tx, so the Tx is always going to be
The same.
Greater.
There's T. The hypotenuse has to be the biggest one, the longest side in the triangle. The Tx is going to be less than. Right?
I said less than.
Yeah, well,
Oh, you got it all in there.
yeah, see this?
Square root Rg tan theta, Megan.
Yep. I wanted to be right today.
How does the pig overcome air friction? We're not sure, but we think it has to do with
The wings.
angular momentum. Angular momentum. Did I show you that video of the Veritasium guy with the big spinning thing, and he lifts it over his head and it goes around like this? Yeah, that's a conservation of angular momentum thing. I used to have a big giant bicycle wheel, and someone stole it off, literally. And you would spin it. Why would you do that? You would spin it, and then you go like this, and it actually, because of conservation of momentum, it's very hard to do. It spins like this. Like, have you guys ever played with the gyroscope?
Yeah.
Same idea how it sort of stays upright, kind of thing. You know, like a gyroscope.
Not like a top.
Yeah, it's like a top. You know how they can kind of, they'll stay upright even though they're leaning over like this?
Come on.
Oh, sorry. Let me see if I can find.